Hello everyone, this is Nicholas from ADC. Last time we did a 2D analysis in XFLR5 for our wing airfoil. Today we're going to continue on and we're going to figure out how to finalize our wing placement so we can make a stable aircraft. So if you remember, we imported our airfoil last time and performed an analysis. Now today what we're going to do, if we hit module and go to wing and plane design, we are actually going to design a plane. So you want to go ahead and hit plane, hit define new plane, and basically what we're going to do is we're going to define our plane in 3D now. So on this file we're just going to use the wing, so we're going to ignore the elevator and the fin, and we're going to define a new wing. And so what this allows us to do is define our wing in 3D using a few different parameters. Firstly, I'm going to go ahead and select the foil. I'm going to use 20 panels in the X direction and 20 in the Y direction. Now I'm going to do cosine for X and uniform for Y. If we look at the panels, you can see that closer to the leading and trailing edge, the panels are more dense, whereas in the middle, they're a little bit less dense. And in this direction, they're more or less uniform. The reason why this is important is because it allows us to optimize analysis time with accuracy. Now, moving on to the settings, this is where what you want to do is you want to go and pull up your sizing. And so what we can do is we can import our chord length and wingspan that we found from sizing. So if I go to XFLR5, this first part is going to be our wingspan. So this is what is called the root. So if I change this, you can see that there's a little gap in the middle. This would be for if you're using a mid-wing design and you have a fuselage in between your two wings. But that gap. Then for the second point, you're going to have, this is going to go up to half of your wingspan. So as you can see, it shows a 1 here, and it shows our wingspan is 2 meters. Because from the sizing, I have 0.9 as my wingspan, I'm going to change this to 0.5, and now my wingspan is 0.9. Moving on, we now have chord. So if I do 0.15 and 0.15, and then do an offset of 0, we now have a rectangular planform. So if you chose a rectangular planform in your decision matrices, then you want to do that here. If you did swept back, you just have the same, your chord length is constant, and then you just apply an offset. So this is what swept back looks like. If you have a trailing edge taper, but not a leading edge taper, then you're going to do a smaller chord with, no, not an offset, sorry. You're just going to do a smaller chord. And you can see, yeah, leave the offset as it is, do a smaller chord. You'll have a constant leading edge and then a tapered trailing edge. And then, if you want to do a tapered leading edge, then you would apply an offset. And that's how you get that. Moving on, we also have dihedral. Dihedral is how twisted the wings are up. So as you can see, if we apply a dihedral of say 10 degrees, there's a pretty extreme amount of up going on there. And so I'm just going to set it to 3 for this tutorial. Yeah, but typically a dihedral is good for having sort of automatic stabilization. So I'm going to go ahead and save that. And then basically what I'm going to do, I'm going to click on my plane, click on analysis, define an analysis, do fixed speed, and now we need to determine what speed we're going to run at. This is what's referred to as the free stream speed. So if we found our stall speed last time from here, so we can define our cruise speed and then make that as a function of stall speed. So what I'm going to do is I'm going to take our stall speed and multiply it by 1.4. Now you can multiply this by 1.5, 1.6. I just estimate for my usage that I can go 40% above. The point of this competition is to go fast, so the faster the better. But for this initial simulation, I'm just going to use 7.3. For analysis, you want to use the ring vortex method and make sure it's viscous. For inertia, just use the plane inertia. For reference dimensions, just keep it as it is. Aero data, that's hit save. And then under analysis settings, if it looks like this, you want to hit sequence and go from 0 to 20 with an increment of 0.5 for your angle of attack. Now, an analysis was completed, but as you can see, there's a lot of these errors where it says could not be interpolated. Now, this is fine as long as you have some data that can be. As you can see, for 8, 8.5, 9, 9.5, etc., it's able to compute the aerodynamic coefficients. So we can go ahead and hit close. Go ahead and save here. And then if we click on this right here, you can actually see some graphs. So what I'm going to do is we now need to find the lift slope. So let me just open up the drive real quick and then go to stability. So the point of what we just did was to find this term right here, this A. That is the lift slope of our wing. So if we go into here, I'm going to add a new sheet. I'm going to call this lift slope of wing. And the way we're going to calculate this is, as you can see, this is pretty linear. We can assume it's linear. So I'm going to find a point. So say 3 as my angle of attack. If I scroll down, I can find the coefficient of lift down here, 0.48565. So I'm going to take that value, and I'm going to plug it into here. And then I'm going to take another value, say 6, and then coefficient of lift is this. And then I'm just going to do rise over run. So rise over, and then it was 6 minus 3, so that would be 3. And so now we have the lift slope of our wing. So now that we did all of that, what we can do is we can do the same thing for the tail. So I'm going to make a new project. Go ahead and open up this is my horizontal tail. I'm going to use the NACA 0010 for that. I'm going to save this as tail. And then I'm going to go direct flow design. As you can see, so I'm just going to go to my and then go here, hit edit in Notepad, go ahead and wait, these values are right. Oh, that's why I'm in the wrong area. Go ahead and open this. There we go. This is a modified version of the DAT file. Go ahead and save this. Then I need to prep the airfoil, so I'll derotate it. I will normalize it, find it globally, 100 points. Then derotate again, normalize. Then I'll go to the analysis, batch analysis, 0 to 20, incrementing, analyze. Cool, analysis completed. Now we can go over to wing and plane design, define a new plane. And so here it's going to be a little bit different. So we're still going to deselect the elevator and fin, and we're going to define a main wing, and we're just going to have that be our tail. So this is our foil. Then we're going to do 20, 20, cosine, uniform. And then now what we need to do is if we go to our tail sizing, we need to determine an aspect ratio. So for this aspect ratio, from there, we can also get horizontal tail chord and horizontal tail span. So for horizontal tail, you should use a ratio below that of the wing. So for the wing, we chose 6. I'm going to choose 3. And then for vertical, I'm going to choose 2. And then I'm just going to go ahead and use the formulas. So for wing, the way you find chord length is just the square root of area over aspect ratio. So square root of area over aspect ratio in meters. And then this is going to be equal to the area divided by this value in meters. Okay, so as you can see, we have a pretty big horizontal tail span. That doesn't seem right. What if I make this 2? It seems a little bit more reasonable. Hold on. Sorry about that, everyone. So now that I've recalculated, calculation was wrong on my end. But now my span is 0.35 around, and then 0.12 for chord is what I'm going to use. So going to XFLR5, I'm going to use a span of 0.165. No, 0.175. Yeah, that gives us a wingspan, or what's a tail span, 0.35, and then 0.12, 0.12, 0 offset, and this will give us our horizontal tail. Notice that we're not going to use any dihedral here. We want this to be flat. And so 20 panels cosine, 20 uniform, and save. Save. Oh, sorry. Plane name. Okay, we can't edit the name. Oh, we can. Here we go. Tail. Just so you know which part you're on. So now we have the tail. We're going to hit analysis, define an analysis. Just use these same settings. Save, analyze, go to the data, and then find the lift slope for this one. So the final part is we're going to take this and we're going to make a big plane, and then we're going to find, so we just found in this equation, you want to use the same method you did on here with this one. So just kind of looking at this graph, you can pick 2 points, look at the coefficients of lift, find the slope. And the last thing we're going to do is going to make a new project. Then we're going to grab these 2 as my airfoils that I'm choosing. No. I'm going to call this plane. Actually, I'm going to go ahead and also grab this for my vertical tail. And so, okay, so it was the 0012 that was making issues. As you can see, we have an issue similar to the Clark Y. So I will fix that and then be right back. Okay, and now we have all of our airfoils fixed. And so we're just going to go ahead and perform the method of fixing them all up as we outlined in the previous part. Derotate. normalize, find locally the 100 points, then derotate, normalize. And the reason why I'm just doing this is just to show you guys, in case you guys are not familiar with the process, we're just making sure that everything's in line with the flow. So there we go. We have prepped all of our airflows. Now we can go into direct flow analysis, batch analysis, and now we select all of the different airflows we want, and then we're just going to hit analyze, and it's going to run through a whole bunch of different scenarios because it has to perform the analysis for each of those three. And you got analysis completed, and you should see 3 different colors. And so now what we're going to do is we're going to go over to wing and plane design and define our wing and plane. So hit plane, define a plane. I'm going to call this plane main wing. We're going to define it as we did on the plane file that we made. So just using the same settings there. So 2 degrees of dihedral, then 0.25, 0.15, 1, that's right, 0.45, wait, that was about right. 1 point. This is my aspect ratio. I see what the issue is. There we go. That looks more reasonable. And let me just verify that that is what I did here. So you can just open up. Yes. Go ahead. You can just hit Control P to open it up as a hotkey. Okay, we did 0.15, 0.1 with the 0.5 offset. Okay. So just open up the plane, and then we'll do that. There we go. There we go. So now we can hit save. Then we're going to define our elevator, span, chord, no offset, using this foil. And that should be fully defined. Great. And then for the elevator, we're going to do kind of a similar thing. Wait, this is the elevator, sorry. For the vertical tail, just going to do this. And then I'm going to change them to that. And then if I repeat my form, and then do area divided by chord. So 0.2 span, 0.1 chord. Sounds about right. Gonna do no offset, just make it vertical. And there we go. We have, wait. Yeah, we have an initially sized into XFLR. So now we're going to do, so we're going to use the lever arm 0.25 and the lever arm is 0.26. Okay. 0.25, very close, 0.26. We're going to make the wing defined at negative, chord is, what's our chord? 0.13. We're just going to divide that by 4. So negative 0.0325. Okay. Negative 0.0325. And then we're going to run with this and probably end up increasing our lever arm. Let's go ahead and save this. And now perform an analysis. That's beautiful. Analyze. Now we can find our last term, which is d epsilon over d alpha. And what that is pick a point, pick another point, and as you can see, this kind of downward curving section is our induced angle. That's our downwash. So we can say that that's negative 1.25 at 3 and around negative 2.4 at 6. So we go, here we go. So you'd fill in the lift slope in the tail, and you'd do downwash per angle of attack, and then we're just going to use the values we found here. So that was negative 2.4, negative 1.25. Oh wait, sorry, we can just, because they're both negative, we just can count as positive, and then we can divide by 3. And so this will get us, actually wait, no, negative plus this, sorry. So this will be our downwash slope, and now we have everything we need to find what is referred to as HN. And so if we look back over here, HN is the distance between leading edge and neutral point, and so we can then use that in our static margin to place our CG. Our CG in XFLR5 we placed at x equals to 0, so we'll move our wing in accordance with that. That was one iteration. Let's go ahead